Okay, so it's not wireless. So these are just a few formulas that they become bigger issue later on. At this point, we just list them. And so sometimes when you do, and especially when you do your project, sometimes this is the very big point, big part of what's going on is to getting from the the derivative to the original function. Okay, and that's what it is. Okay, and now we're moving on to a topic which is different, and that is, I would say, classification of functions, the magnitude of functions. So magnitude of functions. And by which I mean the to begin with, at infinity. So as x goes to infinity, say plus infinity, to just keep it simple, then f of x might go to, say, 0, and then it might go to 1, 2, 3, and it might go to infinity. Okay, so this is the simplest classification you can think of. So it might go to a number, including 0, and then it may go to infinity. So that's the classification that I have in mind, but the problem with this, there are just too many, and especially over here, too many. And this is also too many. In what sense? Different different pace or rate. So because they approach infinity at different rate. Same about zeros. So for example, x and x squared. X squared versus x cubed. That would be a good example of speaking of different rates. So x cubed will go to infinity, x squared too, but x cubed will go faster, right? And then if you flip it, you have 1 over x squared and you have 1 over x cubed. Both of them go to 0. Once again, a different rate, right? So x squared will go to 0 slower than x cubed. Okay, so that's pretty much, we will skip these, but the infinity and 0 is what we might be concerned about. And to put them in, to rank them pretty much is what I have in mind. We already have two, so we start with certainly this one is a simple one, and you can certainly classify them, and this is the sign that we're going to be using to classify the functions based on their magnitude at infinity. Okay, so not saying that one is larger than the other, just but rather whether or not it's large at infinity. So in what sense? This one. And the answer in the sense of their ratio. Okay, so these are simple functions, and then if you look at the graphs, the behavior is very transparent. So x squared versus x cubed will just take off and they never meet together. But if you pick functions more complicated, such as the polynomials that we had, say x squared plus x versus x cubed. Okay, so we add some extra term x to x squared. Does it change anything? Does it change anything? No, x is not a shift. If it was, it's still a worthwhile mention. Okay, how about this one? So this is indeed just a shift. So the answer is then no. Will be no change. So I take that blue one and just shift it by 1. So once again, x cubed will take off and never look back, right? But I could add x, right? And that kind of will look different. That's not going to be a shift. I also could take 2x squared and once again compare it to x cubed. And well, what is your guess about the behavior of these two new functions? Will they fall behind x cubed? Well, actually there is an answer. We sort of saw it previously. Is to rather than trying to subtract, which doesn't really tell us a lot, instead we divide. Okay, so that's the ratio that I have in mind. So divide, and then there should be one should overpower the other. Okay, so in the simplest sense, you just x cubed over x squared is equal to x, and this thing goes to infinity, so that's the end of it. You know that x cubed is more powerful, and not just by a shift. It is more powerful by a ratio. So it will actually, the ratio goes to infinity, but it also applies to, say, 2x squared. It's still x over 2, still goes to infinity. Okay, so once again, it's also x cubed overpowers it. The last one is trickier. No, the second one is trickier, x squared plus x. So what do we do with this one? Remember the trick? From a while ago, you see what we're doing. We're evaluating the limit. We're not evaluating the limit numerator and denominator separately. We know they're both infinite. We're trying to evaluate the limit of the ratio, and we did not long ago. So you see what? How do you remember how we did it? It is a rational function. Well, let me try to refresh your memory. Say x cubed over, well, that's we were computing the limit. So limit x cubed over x squared plus x. X goes to infinity. What is that we're trying to find? Okay, what if I put a square here? What's the limit? No, x squared over x squared plus x. What is the there is a thing in the denominator which is not important. What is it? This one. Why we throw x out? Why? Well, because of the exact reason we just talked about. Because it's x squared is more overpowers x. But generally speaking, the way we have explained it is, we're doing something new, but the way we have explained it is that the leading term, x squared, is the only one that matters. Okay, so this is the leading term, and the rest of the terms don't matter. And that there's only one term in the numerator, so the answer is actually 1 once you throw out the irrelevant stuff. And what we are talking about is, in fact, a horizontal asymptote, if any. Okay, so this particular function has a horizontal asymptote y equal 1. Okay, so that's what we have discovered. But in the original case, x cubed over x squared plus 1, the limit is not 1. But the trick is pretty much the same. So either you look at the leading terms only, these are the leading terms, and based on that, or you do some algebraic tricks, which you will look into later. But so what's the limit? No, x cubed over x squared. Throw out this. What's left? Well, you can do it either literally, or you can do there was a trick. So let's do it. Trick is divide by the highest power. So which is x cubed. So I have x cubed divided by x cubed, and here I have x squared by x cubed plus x by x cubed. Okay, and then I end up with 1, and here 1 over x plus 1 over x squared. Okay, so the numerator now, we have resolved the indeterminate expression. That is the point of this trick, is to deal with infinity over infinity, which is what we're facing. The issue is how to compare two functions, both of which go to infinity, and that if we put them in the form of fraction. But the problem then becomes that we have an indeterminate expression if we want the limit of that. So that's how we use algebraic tricks to deal with those problems, with problems like that. And as you can see, the numerator has no problem anymore. The numerator is and will remain 1. What happens to the denominator? That's right. So this one goes to 1 and this goes to 0. So the whole thing goes where? To infinity. Okay. So and that's it. That's it. Then we conclude that x cubed is more powerful than x squared plus x. Okay. So there is no special word for it, but the notation is the standard notation to indicate that. So that's the notation for the kind of a hierarchy of magnitudes of functions. So if limit f of x over g of x goes to infinity is infinity, then we write f of x larger than g of x. Okay. So and that's the explanation. And then once you have that idea, you can start very easily with this say x squared less than x cubed, and then nth power, and on. All the powers will be, the higher the power the better. And then you certainly can put x here, and then you can put 1. Still works. Okay. What is 1 larger than? Stronger. So in other words, limit 1 over what function will give you infinity as x goes to infinity, if I want to put something here. So we just had that experience right there in the upper right corner. What kind of function you put in the denominator to get the whole thing go to infinity? Any function with 0 limit. Such as 1 over x, for example. So 1 over x is here. And it is stronger than 1 over x squared, stronger than 1 over x cubed, and so on. Okay, so that to begin with, we can demonstrate this very easily through this limit. I mean, the functions are simple enough, so you can put them in the form of when you put them in the fraction, you have simply cancellation. So these are powers. So but there's more to it. There's actually more, because these are only integer valued powers. But you can also pick any other power, such as fractional powers. And by that I mean, for example, square root of x. Square root of x. What is it? What is its power? No, x. The power square root of x is x to what power? 1/2. Okay, so then I'm inserting it. Where do I insert it? First power, and this 1 is actually x to the 0th power, which means that that's where I am inserting it. Okay, so it will be larger than 1 but less than x. It is perfectly visible on the graph. This is y equal 1, and this is y equal x, and this is y equals square root of x. Okay, and then you certainly have x cubic root, which is even smaller, like this, x cubic root, and so on. So there will be more powers, and for every power that you can think of, there will be a function, and they will be filling this hierarchy. So say XR, XS, XS, if R is less than S. Okay, including negative powers. As we saw over there, 1x squared is simply x negative 3, and this is x negative 2. So the hierarchy of the powers gives the hierarchy of the functions. Okay, so that's to begin with, and well, let me to make the picture complete. This is x squared, and then this is x cubed. So these are, you can see how they go into different directions. And well, and then one more is 1x, 1x squared. So they really go in different directions. Okay, so that's to begin with. And then there are polynomials naturally. All the polynomials are now easy to compare, and we have, when we computed those horizontal asymptotes of rational functions. Remember this, and then you're supposed to evaluate this limit as x goes to infinity to find a horizontal asymptote. And the trick is, again, dividing by the highest power. Well, if I put 3 here, then dividing by the highest power will give me 1/2, and that is the horizontal asymptote. But now we know that that really, as far as the which means that in this case these two functions are comparable in the sense that neither one is larger than the other. So these are comparable. Not comparable, but how would you call them? Kind of equal in magnitude. Best we can tell. We cannot really separate them from each other based on their magnitudes, because the limit is 1/2. This is, where is the there's my definition. The notation rather is here. Okay, so that's the important thing to take from this. The rest are just example, but this is really what the informative part. So we take the fraction, and if the fraction is infinity, then we know that then we use this notation and put them one function above the other. The numerator then becomes stronger, is understood as stronger function than g. Okay, but sometimes that's not the case. The limit is a number, and that number is not 0. Then we would say they're equipotent, maybe. Potent. Yeah, I suppose that's a fair term to use. So it's about potency, magnitude of functions, and when the limit is infinite or 0, then we can then it means that they are of different potency. But sometimes it's not the case, as you can see. When we have two polynomials, they have the same leading terms. Then so they are of the same degree. That's the key. Same degree. Same degree. Then the two polynomials are equipotent, even though it's not a technical term. But that's not it. That's not it. There are more functions. More functions than that. And that is, well, let me first, this is also important. That's the only thing that we also know for a fact, a theorem. When we look at powers, we compare them simply by their powers. Slightly more general in some sense, and slightly less general in another. If P and Q are polynomials, then the degree of P larger than degree of Q means that P is more potent than Q. So that's one more theorem. Okay, and this is all these conclusions are based entirely on looking at the fractions according to the definition. This is the definition. We have to look at the fractions and applying the tools that are fairly simple. This is we use the cancellation, And here we used other tricks, division by the highest power. So both of these are certainly come from early in the course. There are more functions. Some of them go to 0, some of them go to infinity. The one good function that goes to infinity is the exponential function. So what about e to the x? So the problem with this is in the fact that well, it is not a polynomial, so none of the tricks will work. So I have e to the x over x squared, and I have no idea where this thing goes. Even though we either want to classify functions as we have been trying to, or it could be simply a function like this, and I want to know what the asymptote is, if any. Plotting this function plotting would actually produce a function that goes to infinity. Okay, so appears to go to infinity, and then you can certainly demonstrate that it does. And the idea is then the exponential function is indeed stronger than any polynomial function, but how do we demonstrate it? And the answer is going back to there is a trick that uses rather than produces any results about the derivative. It uses the derivative in order to discover something about the function. So we're looking at this polynomial, this fraction, f of x over g of x, and we want to evaluate this limit at 0, but so limit goes to what when x goes to infinity. So this is what we're supposed to evaluate. That's our question. So let's make these assumptions about these two functions. F of c is equal to 0 and g of c is equal to 0 at some I'm afraid I'm looking at the wrong place. This is supposed to at infinity, not at, yeah, that has nothing to do with C. That's a typo here. So assume that what we assume is that this is an indeterminate expression. In what sense? Infinity over infinity. So in other words, f of x goes to infinity as x goes to infinity, as well as g of x. Okay? And then this is how we resolve the indeterminate expression. This is how. Then our limit, f of x over g of x, is in fact equal to the limit of the derivatives. Okay, so that's a theorem which is called L'Hopital's rule. So FG are continuously differentiable. Okay. Okay, so that is the conclusion. So so to evaluate remember the derivative is the limit, but instead of using that fact, we turn around and actually use the derivative to compute the limit. So the limit on the left is the one that we want to compute, but we compute it by looking at the limit of the derivatives, which sometimes is simpler. And let's confirm that the conclusions that we have made already. Say I'm looking at the limit of, say, x cubed minus 3x plus 1 over 2x cubed minus x squared plus 1. Okay, so I could just since we have indeterminate expression here at infinity over infinity, right? So I'm allowed according to the theorem. This is the name. according to the theorem, I am allowed to differentiate, but not the fraction. So look carefully. I'm not going to be differentiating this fraction. I'm going to be differentiating the numerator separately from the denominator. So I'm taking the numerator and I'm taking the denominator. Okay? So in other words, this is not the quotient rule. For one reason, I'm not trying to find the derivative of the fraction. I'm trying to find the derivative of the numerator and of the denominator. So 3x squared minus 3 over 6x squared, 6x squared minus 1. 2x. This is a squared actually. 2x. Okay. So I have still an indeterminate expression, because I still have infinity over infinity, which means that I could apply L'Hopital's rule again. Okay? And how I once again differentiate each of these. Either the numerator and denominator. Okay? So and then it's going to work out this time. No, I might have to do it one more time. So I have 6x divided by 12x minus 2. Okay, so at this point I either do the some other tricks that we know, or I do L'Hopital rule one more time. And if I do it one more time, I'll have limit 6 over 12, which is 1/2. Okay, so the result is the same, and that is just a little computation to confirm that we know what we're doing. And the result certainly works out the same. We could have accomplished the same goal by simply looking at nothing but the leading terms, right? So it's 1/2. That's it. But the true applicability and value of the rule is to deal with functions other than polynomials. And so this is the one that we already looked at, e to the x over x squared. Okay, so then there is no other trick available to us that would allows us to use L'Hopital to compute the limit. Okay, so and then this L'Hopital's rule really shines. It really shines here. So indeterminate expression again, infinity over infinity. So L'Hopital's rule applies, and I differentiate these two, e to the x prime, x squared prime, and what I have here is that's the thing. What happens to, you can see that what's happening is that the exponential function's derivative is the same function, so no trouble. Nothing happens. In the meantime, something has happened in the denominators. The denominator went down by 1 in the power. It doesn't solve the problem just yet because we still have an indeterminate expression. E to the x goes to infinity, 2 to the x goes to infinity. So the problem has not been solved, but on the other hand, every time it's not solved, it means that the L'Hopital's rule is applicable. Okay, so and we apply L'Hopital's rule again. And we differentiate these two again, e to the x prime, 2x prime. And I have then limit e to the x over 2. So what's the answer? Infinity. So then we conclude, according to our definition, that e to the x is stronger than x squared. Okay?
You can do that, the L'Hopital's rule for as many times as you need until you get it.
Yeah, as long as every time you have an indeterminate expression. So then you can imagine e to the x over x cubed. What's the limit? So once again, infinity. So in fact, how you get there, you instead of using L'Hopital's rule twice, you'll use it 3 times, right? And then any power, then e to the x is stronger than any power, right? So it doesn't matter. You just have to use L'Hopital rule enough times. which is certainly requires some getting used to, because a very high power numbers will be working against you. If you start with x, it will go fast, while exponential function will be early on kind of slow. But as you move away, increase x, the scale out, exponential function will always overcome the power function, no matter how large the power is. So that's a nice tool for our purposes. And there's similar versions. There are similar versions of L'Hopital's rule for the rest of the for example, to begin with, for other indeterminate expressions. So this is an indeterminate expression of this, whereas the indeterminate expression is this. This is the indeterminate expression. So it will give me infinity over infinity, and under these circumstances I am allowed to differentiate these two to find out what happens. But another popular indeterminate expression is 0 over 0. So that is, remember what we try to classify over here. In addition to infinities, over here there are functions that are actually small. They go to 0. And once again, we can ask ourselves, does it go to 0 fast enough, or fast in comparison to another function? It is easy to compare 1 over x or 1 over x squared with each other, but anything more complicated, such as might be problematic, even though not really necessarily hard. So, for example, if I have the exponential decay compared to any polynomial decay, so e negative x, for example, okay, and I compare to the 1 over x decay, which is just a regular 1 over x function. So which one goes faster to answer? So to compare, you have to evaluate the limit of e negative x over 1 over x. X goes to infinity. Okay, so one way it is indeterminate expression 0 over 0. So L'Hopital's rule as it stands cannot be applied. But really, we could, if we just tweak the algebra a little bit, we could reduce the problem to the previous one. So I'll have simply limit. Do you see what I'm going to do here?
You put x squared over edx.
No, I don't want to differentiate. I mean, I could, but you can see how I can handle it without differentiation. Well, let me do L'Hopital's rule first. If I try to differentiate, then look what happens. If I differentiate numerator and I differentiate the denominator. So I'm applying L'Hopital's rule. It is okay because it's 0 over 0. It is the version that I haven't written yet, but it is another version. So I'll have limit, and I have okay. What's the derivative of e negative x? Not quite. E negative x with something. It's the chain rule. Minus. That's right. The derivative of negative x is negative 1. Okay. What about the denominator? Derivative 1 over x, if you remember what? No, just the derivative of 1 over x, what is it? If you don't remember, do you? Negative 1 over x squared. Remember, the power goes down by 1. Okay, so so even if I get rid of the negative signs, you see my problem. This is, you see what happens to the denominator. It's not gonna get any simpler. It's not gonna get any simpler the way it did over here. As you can see, you start with x squared, and then you differentiate once or twice, as many times as it takes, and then you end up. This is the point where we would like to see, so that it simplifies to such a degree then it does not affect the limit, and then we know the limit. It's not going to happen here. Oh, we differentiated once, and the degree went down by 1, but it did not disappear. And if we keep differentiating, it will be just the negative 1 over x cubed, 1 over x fourth. So that's the dead end. So L'Hopital's rule here gives me a dead end, even though under different circumstance might be better. But here we could try algebra instead. So e negative x over 1 over x. What should I do with 1 over x?
You get x out in the denominator.
Yeah, okay, so what do I get?
X e to the negative x.
Okay, so that's good, but not as good as we would like to have it, because we don't have a fraction. Can I turn it into a fraction?
X over e to the x.
That's right. Okay, and do you know what this limit is?
If we go to 0.
0, that's right, because we looked at its reciprocal, right? And it was infinity, so now the limit is 0. Okay, so also then we demonstrated by computing this limit with these functions, we actually found out something about those. So the conclusion is that e negative x is smaller in the sense that it goes faster towards 0 than 1 over x. Okay, so the decay is faster than just the polynomial, just as the reciprocal number. So there, yeah,
So whenever it's infinity over infinity with our indeterminates,
yeah.
would it be smart to just use L'Hopital's rule if all of
If it works, then it works. The people love L'Hopital's rule because it's just if you already know how to differentiate, it comes very very handy, and you just apply it. So if it works, you can feel free to use it. But it is the admonition is always verify that it is an indeterminate expression, because if it's not, then it will just give you results that are entirely wrong. So I don't know, x squared. Hold on a second. Well, it could be a very, very simple, actually. Say x over 1. X over 1. Okay, so if I try to use L'Hopital's rule, I'll have 1 over 0. Right, okay, so that doesn't make any sense whatsoever. Yeah, so you just have to verify that indeterminate expression, as well as differentiability, but that is always, or usually is okay, is visible right away. So there is also an analog of L'Hopital's rule for points rather than horizontal, rather than infinity. So we have, just as we have horizontal asymptotes, we have vertical asymptotes too, and we also have had indeterminate expressions, but in a different way. Not a lot actually, but say so once again f of x over g of x, but this time the limit is x goes to, say, some value c. Maybe from one direction, maybe from left or from the right. In other words, what we're asking ourselves, this is x equals c, and the limit might exist, or it might not exist, and you might have a vertical asymptote. So these are the two possibilities. Even though, and once again, it only makes sense to invoke L'Hopital's rule when you have indeterminate expression. So we have done it before without L'Hopital's rule, but let's see, I wonder if you remember this one, x squared minus 1 over x minus 1. That's a typical example. These are the two functions, and x goes to 1. Okay, it is indeterminate expression, right? So L'Hopital's rule applies, but let's ignore that. You remember how we handle this limit? What?
x minus 1.
Right.
Factor in.
We factor the numerator. Okay, and then we delete it or cancel it. X plus 1, x goes to 1, and the answer is 2. Okay, so in other words, we have a hole in the limit exists, so we have a hole in the domain, but otherwise it is a removable, what's called removable discontinuity. There is only one point missing. Okay, so now let's try L'Hopital's rule instead. So and it is an indeterminate expression, so I could differentiate. So x squared minus 1 prime over x minus 1 prime. So I'll have 2x over 1. And we do have 2. Okay, so that works out. Certainly it is just as interesting situation when you have a vertical asymptotes at a location. I have an example here somewhere. Alright, maybe I don't. For some reason I don't have. There are all kinds of weird indeterminate expressions that I don't want to go into. Okay, it is dead now. Out of power. So 0 is 0, infinity over infinity, but then there is also infinity minus infinity, and 0 to power of 0, and then there's a bunch of these, and they're all these two are just as not necessarily common, but they're certainly just as troublesome as the other two, but they cannot be subject to L'Hopital's rules, because L'Hopital's rule is about the fraction. So you have to convert them into fractions in order to apply L'Hopital's rule. And how do you convert subtraction into division? There is a function that does it. Oh, the addition, subtraction versus multiplication, division. Does it ring a bell? Yeah. So in the left-hand side of the formula you have addition, in the right-hand side you have multiplication. So what am I talking about?
It's late.
Okay, it's a logarithm. It's a logarithm. So that's how you convert it if necessary. All right. So I don't want to go there, but just enough said that you can do it if necessary. They say limits like x, 1 of x. That kind of limit. X goes to infinity or to 0, and once again you could use L'Hopital's rule, but only if you apply logarithm before or after. So anyway, there are actually more important things. This is a very computational thing, and it's when it comes handy and you know how to do it, you feel very happy. But really, there are complex concepts and ideas that we have to discuss that are actually more important than this. The only thing that is worth mentioning is why does it work in the first place? So why the L'Hopital's rule works, like this limit f of x over g of x. How is it possible? What is the relate to c, say, is equal to limit f prime of x over g prime of x? It appears to be kind of a strange thing to imagine, but actually it is believable if you just tweak the formula a little bit. So first of all, we know that f of c is 0 and g of c is equal to 0. So that's the indeterminate expression 0 over 0 specifically. Okay, with that I could rewrite the first expression as this: f of x minus f of c divided g of x minus g of c. It's 0 anyway, right? Okay, and then I do a little bit more, limit, and I introduce the x minus c here. So I divide both by x minus c, numerator and denominator. So it will be f of x minus f of c, x minus c, and then what I divided by is g of x minus g of c divided by x minus c. Okay, and at this point you just recognize these two expressions. What are these expressions?
So rates of change.
The rates of change, yes, they are rates of change of these two functions, and their limits are the derivatives, right? So this will be f prime of c, and this will be g prime of c, and indeed we have arrived to our L'Hopital's formula. So there is a little bit more to it, but that's pretty much it. So I think since I don't have any of my notes left, I think I just stop here. Unfortunately, I just let it expire.